Good evening, everybody. Okay, I welcome you to another online review session on a Sunday night. And for today's review session, we are going to review for the third exam that is scheduled for Tuesday, November 19. And for this review session, we are going to use the previous exam 3, which was taken in fall 2012. I do notice that a lot of you have joined us today. However, in the interest of time, so we could save some time, I will be acknowledging some of you most of you during the course of this session. So what I would like to do now is go straight to today's set of questions. Okay, Kiara, can you go ahead and read this question for us? Okay, I think Kiara might be having problem with her mic. Marcia K, can you go ahead and read this question for us?
Each of the following transformations may require one or more steps.
Okay, thank you. Continue.
Each of the following transformations. Can you hear me?
Yes, I hear you.
Can you hear me?
Yes, I hear you. Go ahead.
Each of the following transformations may require one.
Okay.
Each of the following transformations may require one or more steps. Provide the required.
Okay, thank you. I think Kiara might be having problems with her mic. Okay, thank you. That was good. So, okay. Now the question is, each of the following transformations may require one or more steps. Provide the required reagents for each transformation. Now, this set of questions here, you can see here, our focus is on this carbon-carbon triple bond. And what they want you to do here is to transform this carbon-carbon triple bond to each of these classes of compounds right here. Now, so what I want to do, instead of using an R, which is this generic R here, I'm going to use a specific alkyl group so that we could transform a terminal alkyne to each one of these. Specifically, this question is testing your knowledge of the reagents. It is also testing your knowledge of the synthesis of the different classes of organic compounds. Okay, so let us start. What I'm going to do now, let me go ahead and number this. I'll say this here is 1. This here is 2. This is 3. This is 4. This here is 5. This is 6. This is 7. And this is 8. Okay? So now what we want to do now, let us work on transformation number 1, going from a carbon-carbon triple bond to this organo halide compound right here. Okay, one thing we do know, so let me do this. Let me say 1. Instead of the R, let us just simply use a methyl group. The R could be any alkyl group. You want to take a carbon-carbon triple bond. What they want us to do here is to transform this carbon-carbon triple bond to this alkyl halide. Now we do know that there is no reagent that would directly transform a carbon-carbon triple bond to an organohalide. Therefore, this must be a multiple-step process. We also know that to make this kind of organohalide, we could use an alkene. So therefore, this first thing we need to do here is to transform the carbon-carbon triple bond to a carbon-carbon double bond. So what reagent do we need to do that? To go from a carbon-carbon triple bond to a carbon-carbon double bond. What reagent do we need to do that? Anybody else? Okay, hydrogen and Lindner. Excellent. Excellent. Somebody have their mic off. Can you turn your mic off, whoever has their mic on? Just turn it off. Okay, so we need hydrogen. And Lindner catalyst. Okay, what other reagent can we use? What other reagent can we use? Anybody has an idea? To go from a carbon-carbon triple bond to a carbon-carbon double bond. Okay, excellent. Okay, lithium in ammonia. Okay, those are the kind of things you guys need to know. You need to know your reagent, or lithium in ammonia, or you could also use sodium in ammonia. Okay? Okay, so all of these reagents here will transform the carbon-carbon triple bond to a carbon-carbon double bond. Now, to now go to this compound here, what reagent do we need? This is what they want us to do now at this point. Okay, to go from a carbon-carbon double bond to an organohalide, an alkyl right here. What reagent? Okay, HCl. Excellent. Somebody said HCl. And that is a Markovnikov addition of hydrogen chloride. Excellent. Okay. So this is a case of knowing your reagent. Okay, so this is a Markovnikov addition of hydrogen chloride across the carbon-carbon double bond, in which case the hydrogen comes to this carbon here, and the chlorine comes to this carbon. So we say this is a Markovnikov addition. Okay, so that is good. Okay, now let us go to number 2. Let us go to number 2. Going from this carbon-carbon triple bond to a primary alcohol. Okay? So let us use another alkyl group. Say, for example, we could use this alkyl group to represent your R. This could be the R right here. So we have a carbon-carbon triple bond. Okay? Now, we do know that we do not have a reagent that will transform a carbon-carbon triple bond to a primary alcohol. We know that we do not have a reagent that will do that. So therefore, this transformation here, number 2 transformation right here, must be a multi-step synthesis. So therefore, we also do know that we could make a primary alcohol from a carbon-carbon double bond. So therefore, just as in the case of the first question here, we do need to make the alkene first. Okay, so you guys have already given us all of these reagents to transform a carbon-carbon triple bond to a carbon-carbon double bond. So let us use any one of them, hydrogen and Lindner. And so therefore, that will give us this product here. Okay, so we get an alkene. Now from an alkene to go to here, what reagent do we need now? Keep in mind now we need to form a primary alcohol, which will be this here. Now, what reagent do we need to use right here? Going from here, carbon-carbon double bond to a primary alcohol. Okay, very good, very good. Somebody said BH3 followed by hydrogen peroxide. Excellent. Now, folks, when you do that, that is good. When you use this here, make sure you indicate the sequence. In other words, you add the borane first, BH3, followed by, then you say step 2, hydrogen peroxide in hydroxide. Okay, you need to say step 1 and step 2, because if you don't do that, you will be losing some points. Okay, so make sure you indicate the sequence 1 and 2. Okay, so this is an anti-Markovnikov addition of water. As you can see here, this is an anti-Markovnikov addition of water. Addition of water across the carbon-carbon double bond. In this case, the hydrogen goes to this carbon here, and the OH goes to this other carbon. In the anti-Markovnikov addition, the hydrogen goes to the carbon that contains less number of hydrogen. Okay. Okay. So now we've done 2. Now let us do 3. Let us do 3. Let me erase this. Now let us do 3, which is this here, going from a carbon-carbon triple bond to an alkyne, an internal alkyne. You know, in other words, you are adding we are going to form a new carbon-carbon bond, adding a methyl group to this carbon here. Okay. What reagent do we need to do this? Well, let us use this molecule here. Let us use this alkyne. Supposing we use this one here, benzene attached to a carbon-carbon triple bond. Okay. And what do they want us to do? They want us to make this. Okay, anybody has an idea what reagent we need? We need to form a new carbon-carbon. Excellent, excellent, excellent. Yes, excellent. Okay, all of you said, some said sodium amide followed by methyl bromide. Another person said potassium hydroxide followed by methyl bromide. All of those are correct. Very good. So you do need to know your reagents. So here, sodium amide. Once again, you got to show the sequence. That is step 1. Then you say step 2, methyl bromide. This is an SN2 reaction. Because what the sodium amide does is to remove this hydrogen here, and then you are going to form an acetylide anion. The sodium amide or the potassium amide comes in, remove the terminal hydrogen from the terminal alkyne, and you form this acetylide here. Okay, now this acetylide anion now could act as a nucleophile to displace the bromine from methyl bromide. So this is a classic SN2 reaction. Okay? Okay, so that is the reagent for that, sodium amide followed by methyl bromide, or you could use potassium hydroxide followed by methyl bromide. Okay, so that is question number 3. Okay, somebody has a question. Do you need to include ammonia also? Yeah, in the case of sodium amide, if you simply just use the sodium amide without the ammonia, that is fine. But if you want to include the ammonia, that is also okay. Okay, let me take this off. So you could see here, these questions are actually very easy once you know your reagents, and that is why I keep telling you guys you need to know your reagents, okay? Okay, so now let us do number 4. We did this already. Okay, number 4, this right here. So number 4, what does number 4 tell us to do? We want, okay, let me use this Alkyne. Okay, supposing we use this, and then what they want us to do, they want us to make this. Actually, so that, let me make this ethyl. Let me make this an ethyl group. Okay, so now they want us to make this. So they want us to make this methyl ketone. Okay, do we know a reagent that will transform directly a terminal alkyne to a methyl ketone? Anybody has an idea? Okay, excellent, excellent. Mercury sulfate, okay, or any mercury 2 salt will do. Okay, so here, okay, so you guys are getting ready for this exam. Believe me, once you know your reagent, you will not have problem. Okay, and this is the reagent that will transform a terminal alkyne into a methyl ketone. Okay? Okay, so that is 4. Now let us do 5. What does 5 say? 5 wants us to go from a carbon-carbon triple bond to an epoxide, okay? So let us use this for our R group. Keep in mind, all I'm doing here, simply just changing the different, using different R group, okay? So here, we have a carbon-carbon triple bond. And now they want us to make this epoxide here. Okay. Now, we do know that we do not have a reagent that will transform a carbon-carbon triple bond into an epoxide. So therefore, this must be a multiple-step synthesis. However, we know that we could use an alkene, which is a carbon-carbon double bond, to make an epoxide. So therefore, the first thing we need to do here is to make the carbon-carbon double bond, and then we take it from there. So let us make the carbon-carbon double bond. You guys already know what reagent to use for that, so okay, you guys already told us you could use lithium in ammonia, or sodium in ammonia, or hydrogen with limla. So any one of those reagents would transform a carbon-carbon triple bond to a carbon-carbon double bond. Now, to go from the alkene, this here, to the epoxide, what reagent do we need? What reagent do we need to do that? Anybody has an okay, MCPBA, excellent, okay, good. Oh, okay, and somebody said bromine, water followed by sodium hydroxide, excellent. Both of those are correct. Okay, excellent, excellent. Okay, that is what you need to do. You need to know your reagents. Okay, let us have this here. Once you know those reagents, these things are very, very easy. Okay, so what do we have? We have what you do here, you use M-chlorobenzoic acid, say MCPBA, that will transform a carbon-carbon double bond to an epoxide. You could also use this, the sequence of reaction in which you have step 1, you use bromine water, and then step 2, the bromine water, you react, the product of the bromine water, you react with sodium hydroxide. Okay, and you will get the epoxide. Now, let me refresh your memory here. Oh, I'm sorry. I don't mean to use that on the alkene. I mean on the alkyne. I mean to use it on the alkene. Okay. I want to say, okay, with this here, I mean to say that you use this here. Okay. Okay. Now. What the bromine water does, the bromine water will react with the carbon-carbon double bond. If you recall, to form what we call a bromohydrin. Bromine water or chlorine water, what they do is to add bromine and hydroxide across the carbon-carbon double bond right here. You see right here, the OH comes here, the bromine comes here. And now, what the hydroxide will do, the hydroxide acts as a base to abstract this proton here, and this electron goes to oxygen, and then you have this intermediate. Now, this intermediate now, which is an alkoxide, ion, because you have negatively charged oxygen, what this now does, this alkoxide now will attack this carbon here. So this is an SN2 reaction, attack that there, and that is how you get this. So this is what we will refer to. This is what we will refer to as an intramolecular SN2 reaction. You see here, SN2 reaction, you have a strong nucleophile, and then you have a primary substrate in which the leaving group is attached to a primary carbon. So this is an excellent case for an SN2 reaction. Okay? Okay, so now we've done 5. Let us go to 6. Okay, let us go to 6. Okay, in 6, this should be fairly simple. We are told to go from a carbon-carbon triple bond to a carbon-carbon double bond. So what reagent do we need for this? Everybody should be able to get this. What reagent do we need for that? Okay, let us use this. Okay, you could use Lindlar. Excellent. Excellent. You could use Lindlar. You could use hydrogen with Lindlar catalyst. And that gives you this here. What that does is simply to add 2 hydrogen atoms across this carbon-carbon triple bond, and then you get your alkene here, carbon-carbon double bond. You could also use lithium in ammonia or sodium in ammonia. Okay. Okay, so let us do we've done 6, let's do 7. Everybody should be able to get 7 also. Hopefully this is will be a very good review for you, because this particular problem here gives you a chance to review a variety of reagents. Okay, so 7. For 7, okay, they want us to go from an alkyne, carbon-carbon triple bond, to an alkane. Okay, so we could simply use this here for the R group. Okay, so what reagent do we need? Okay, good. Oh, no, not Lindlar, not Lindlar. No, okay, you need your regular hydrogenation. Okay, in this case now, you have to use your regular hydrogenation, palladium over carbon, or hydrogen over platinum, okay? Or, yes, you could also use platinum oxide also. Excellent, excellent. Okay, so now let us do the last one on this problem, which is 8. Okay, for this, they want us to go from the alkyne to this aldehyde here. Notice here, for this problem here, this carbon here is this carbon, okay? Because this is an R and this is this R here. So therefore, we are going to lose this carbon. Somebody say for number 6, can you use lithium in ammonia? No, lithium in ammonia can. Yes, you could use lithium in ammonia for number 6. I thought I said that also. Yes, you could. Okay. So here, so therefore, in this particular problem number 8, we are going to lose this carbon. So, but we do not have a reagent that will do that directly. So this therefore tells us this must be a multi-step process. So, but we do know how to make an aldehyde from an alkene. Okay, so the first thing you want to do therefore is to take, because use this carbon-carbon triple bond, use this molecule here. This is our R. So the first thing we want to do is to make our alkene, carbon-carbon double bond. Okay, Lindlar, excellent, excellent, very good, very good. So you guys it seems to me you guys are almost getting ready for this exam. I see that many of you know your reagents. Okay, so you form the carbon-carbon double bond, and then after that, what reagent do we need to use to get this? Okay, excellent. Ozonolysis. Okay, yes, all of you got ozonolysis, right? Because what you have to do here, this carbon here is going to be this carbon. So you have to clip this carbon-carbon double bond, and the reagent that will do that is ozone followed by zinc. Okay, excellent. Okay, so this here is step 1. Keep in mind, make sure you indicate the sequence so you do not lose any point. Ozone followed by zinc in some acid. Okay? Okay, now folks, we have finished our problem number 1. So let us go to the next one. Okay? Okay, Mashike, can you go ahead and read this question for us?
Provide the reagents that will transform cyclopentene to each of the following compounds.
Okay, thank you. Okay, now what this problem is also testing here is also testing your knowledge of the reagents. And also, of course, it is also testing your knowledge of nomenclature. Okay. Okay. So it says provide the reagents that would transform cyclopentene to each of the following compounds. So let us start with A. We have cyclopentene. This is another case of knowing your reagent. Cyclopentene, and we say we want to make this here. So in other words, we are going from an alkene to an alkyl chloride in an organohalide. What reagent do we need? Anybody? Okay, HCl, excellent. Okay, hydrogen chloride. HCl will add hydrogen and chlorine across the carbon-carbon double bond to form an organohalide. In this case, an alkyl halide, alkyl chloride. Okay, so that is A. About B. For B, says we need to go from cyclopentene again. Somebody has a question for me. Will we have to draw the cyclopentene and the product on the exam, or simply list the reagent? In this case, I want you to give me the structures. Okay, not just the reagent. I do want you to give me the structure. Okay, so you need to give me the complete reaction. Okay. Okay, so we have here again. We have this. And then it says okay, so now what reagent do we need to make this? Bromo, MBS, very good, MBS. N-bromosuccinimide, okay? Okay, N-bromosuccinimide, excellent, very good. N-bromosuccinimide, what it does is to replace the allylic hydrogen with a bromine, okay? That is what the MBS does. And if you look at this molecule here, we have allylic hydrogen here, we have allylic hydrogen here. So this happens to be a symmetrical molecule. So you could replace any one of these hydrogen on this carbon or on this carbon, you will get the same product. Okay? Very good. Now let us do C. C says pentyl cyclopentane. Okay, so we need to go from here to here. Pentyl cyclopentane. Okay. Okay. Now, how do we do this? We are forming a new carbon-carbon bond. Okay, this will be a multi-step. If you can see here, obviously this must be a multi-step process because we are going to form a new carbon-carbon bond. So what I need to ask yourself is, what are those reagents that you know that will form new carbon-carbon bonds? How do we approach this? Okay. Okay. Yes. A Gilman reagent. Very good. Okay, but before you make the Gilman reagent, that's excellent. You need to use the Gilman reagent. But before you do that, so I will say to make this here, this is question C. Multi-step process. Okay, so the first thing I need to do, of course, I need to make the alkyl chloride. Once you make the alkyl chloride, now you could now take the appropriate Gilman reagent. For the exam, you could simply just use an appropriate Gilman reagent. You don't need to make the Gilman reagent yourself. Okay? Okay. So that would be an appropriate Gilman reagent, because what happens, the Gilman reagent here, this alkyl group behaves as though it is a nucleophile, as if it is a nucleophile, and it will then attack this carbon here. This will be your another SN2 reaction. This is another SN2 reaction, in which the alkyl group on the Gilman reagent is acting as a nucleophile. Consider that this carbon here is negatively charged, and then that will attack this carbon here, because this chlorine will be a good leaving group attached to a secondary carbon, and that will be one of those examples of an SN2 reaction to now form this. Okay? Now, about D. For here, they also want us to go from here to here. Okay? So this is another case of making a new carbon-carbon bond. So what do you think we need to do here? You have to make a new carbon-carbon bond. Okay, exactly. Okay, you add hydrogen bromide. Okay, great, we could do that. And then followed by what? Exactly. Then you use your the Gilman reagent. Excellent, Gilman reagent. Okay, so we could take this. This is for D. So we could take this here, react with HBr, or we could react with hydrogen chloride. This can let us use hydrogen bromide, and then you get the bromocyclopentane, and then you simply now use an appropriate Gilman reagent. Okay, Now that Grignard reagent will simply now give you this here. Okay, this is another case of an SN2 reaction. Okay, so we have finished our question number 2. So we are moving right along. Okay, go to the next one. Okay, not that one. Okay, let's try this again. This is another case of reagents. So this here, everybody should be able to do this. Okay, let me see here. Danutika, can you go ahead and read this for us?
Provide reagents for each of the following transformations.
Okay, thank you. Very good. Okay, now, so this is another case of testing your knowledge of the reagents. So, folks, you see, a lot of these questions is just knowing your reagents. Okay, so let us do A. What do they want us to do? Go from this terminal alkyne to a methyl ketone. So, what reagent do we need? I think we've done this already. Yes, very good, very good, very good. Mercury sulfate in the presence of dilute acid. Could be sulfuric acid. Yes, that would be good. Okay. So this reagent here, what it does is to transform a terminal alkyne to a methyl ketone. Terminal alkyne to a methyl ketone. And that is what this reagent would do. Okay. How about B? At this point, the same terminal alkyne or another terminal alkyne, now we want to transform to an aldehyde. Okay? To aldehyde. What reagent do we need to do that? What reagent do we need to do that? I know you guys know this reagent, this one here. What reagent? Okay, oh, exactly. This is boration oxidation, borane followed by hydrogen peroxide. Okay, very good. So here, now don't forget to give the sequence here. The first step is BH3. Then second step, make sure you show the sequence, step 1 and step 2. Do not just add both of them at the same time, because that way you will lose some point. Okay? And what this reagent will do, BH3 followed by hydrogen peroxide in base, is to transform a terminal alkyne to an aldehyde. This is an aldehyde right here. Okay, this is just the condensed form of the aldehyde, the way it is written. Okay, so that's an aldehyde. Okay, now let us do the last one, C. Here we need to form a new carbon-carbon bond. You can see here, this terminal alkyne, now we're now forming an internal alkyne. In which we have extended the chain by a methyl group. So what reagent do we need for this? Going from here to here. Okay, sodium, very good, very good. This here, sodium amide, step 1, keep in mind, show the sequence. Do not just write both of them together. And then followed by methyl bromide. This is another case of an SN2 reaction. This is also an SN2 reaction. Because if you recall, what the amide does is to pull off this hydrogen here. What the amide does is to pull off the hydrogen from a terminal alkyne What it does to form this, Okay, so that becomes a nucleophile. That is your acetylide ion. And then this nucleophile now comes in to attack the methyl group, and then the bromine leaves as a leaving group. And you know that the can you hear me? If you can hear me, give me a happy face. Okay, good. Everybody can hear me. Okay, very good. Okay, I'm glad you can hear me. Let us go back to the section. Okay, what I just did there, I lost my internet. Okay, is everybody with me? Okay. So now, what we have here, so I was telling you that this is another case of an SN2 reaction. Once you form the acetylide anion here, that comes in to attack this methyl group, and then the bromine leaves as a leaving group. Okay, so we've done number 3. Let us go to the next one. Okay. Sean, if your mic is working, can you read this question for us? Okay. Maybe his mic is not working. Okay, Annette, is your mic working? Can you read this for us? Okay, maybe those mics are not working. Ronel, can you read number 4 for us? Okay.
Provide reagents for each of the following transformations.
Provide reagents for each of the following transformations. Am I talking?
Okay, thank you. Okay, that was, I heard you, Sean, I also heard Ronel, both of you at the same time. Okay, thank you. Okay, so what this question is asking us to do here, provide reagents for each of the following transformations. You can see here, this is another case of knowing your reagents. Okay, so let us do this. Going from a carbon-carbon double bond, forming a secondary alcohol, what reagent do we need for this? Okay, what reagent do we need for this? If you can see here, this is an anti-Markovnikov addition of water. Anti-Markovnikov addition of water. Okay, of the elements of water. So, that means the hydrogen comes here, the OH comes here, and that's why we get it. So what do we need? Okay, very good. BH3, step 1, followed by hydrogen peroxide in basic medium. Okay, very good. Okay, about B. Now B wants us to go from a secondary alcohol to a secondary alkyl bromide. What reagent do we need here? Okay, PB, okay, phosphorus tribromide. Now you see how easy these problems are once you know your reagent. Now what do we need to do here? We're going from the secondary alkyl bromide to, we are now forming a new carbon-carbon bond. What reagent do we need here? C. What reagent do we need for C? Gilman, excellent, Gilman reagent. So here, to C. Okay, so once you know your reagent, believe me, most of the problem in organic, I will tell you 70% of the problem in organic chemistry will be easy for all of you guys. You need to know those reagents. Nobody can make you know them except yourself. Okay, you got to commit them to memory. Okay. Okay. Now let us see here. Ronel, go ahead and read this for us again, since I called both of you the last time.
Methanol reacts with 1-bromo, 1-methyl cyclohexane to give 1-methoxy, 1-methyl cyclohexane. Provide a mechanism for the reaction.
Okay, thank you, and very good. Okay, I'll turn your mic off. Okay, so here the question is, now this is a question of reaction mechanism. I want to go over this again. I know we did this in class for the benefit of all of you again. Okay, it says methanol reacts with 1-bromo, 1-methylcyclohexane to give 1-methoxy, 1-methylcyclohexane. Provide a mechanism for the reaction. Okay, very simple. Okay, so what do we have? We have this 1-bromo, 1-methylcyclohexane. One bromo, 1-methylcyclohexane, and it says it reacts with methanol. To give this. And that is the 1-methoxy, 1-methylcyclohexane. Now I say provide the reaction mechanism. Okay, so let us give the mechanism for this reaction. Okay, before we give the mechanism, what kind of mechanism, what kind of reaction is this? Anybody has an idea? Okay, SN1 reaction. Excellent, excellent. This is a classic SN1 reaction. Classic SN1 reaction. You know. Okay, why do you say this is a SN1 reaction? We know it is a substitution reaction, but why the okay, tertiary carbon? Exactly. Because this leaving group here is attached to a tertiary carbon. Anytime you have a substitution reaction in which the leaving group is attached to a tertiary carbon, that will be an SN1 reaction. Okay? Okay, so let us do that. So the first thing that happens here, in the SN1 reaction, the first thing that happens is that the leaving group will break away from the substrate. Okay, so you are getting, notice what I'm doing here. This arrow here simply tells us these two a pair of bonding electrons here will be pulling away to bromine. Thereby, you are going to form a carbocation. In this case, we form a tertiary carbocation. So we form a tertiary carbocation. And this is the limiting step. You need to indicate this is the limiting step. Okay, this is the rate limiting step. Rate limiting step. Notice here, you do not have to write the transition state. Let me repeat. When you write the reaction mechanism, nobody is asking you to write the transition state. Do not do that, okay? Just show the formation of the carbocation. Now, the next thing that happens in this case, the methanol now comes in as a nucleophile. To attack the carbocation. Okay? The most important thing to do here, once you form this here, you need to indicate that this is the rate limiting step. Okay? Then you follow that up with the attack of the nucleophile on the carbocation. So you now form this. This oxygen now is positively charged because it is using one of its non-bonding pair of electrons to bond to this carbon here. Now, what is now going to happen? Remember that we started off this bromine leaving, so the bromine is still here. That bromide now, the bromide now comes here to abstract this proton from this oxygen, okay, thereby releasing this pair of bonding electron here to oxygen. Notice how I am carefully drawing these arrows. You must draw those arrows because that is the essence of your reaction mechanism, showing your arrows, the movement of electrons. Okay, now we get this. You notice in this particular reaction here, there is no need to show stereochemistry because we are not starting with a chiral molecule. This molecule is not chiral. This is an achiral molecule. So there is no need to show stereochemistry here. So anyway, what I've shown you here, this is the reaction mechanism. This is your reaction mechanism. Okay, you notice there is no need to draw the transition state. Okay, so let me write that because in the last quiz that you guys did, a lot of you keep spending a lot of time trying to draw transition state, and that was completely unnecessary. No need for drawing transition state. Okay, now let us go to the next. Okay, somebody ask a question for me? No, no question. Okay, let us go to the next one. Okay. Okay, 7. Let us see here. Okay, Lorraine, can you go ahead and read number 7 for us?
Compound A reacted with 3 equivalents of hydrogen to give compound B. Compound A also reacted with NaNH2 followed by bromomethane to give compound C. Compound A is also known to contain a cyclopentyl ring. Finally, compound A reacted with KMnO4 to give a ketone plus other compounds. Provide structures for compounds A, B, and C. Also write the reactions.
Okay, thank you. Okay, very good. Okay, so this is one question here where you now have to begin to think. Okay? In addition to knowing your reagents, now you have to begin to use your critical thinking skill. Okay, so we call this roadmap problem. Okay, so let us start. We have compound A. Let's start on this side. Compound A. The formula for compound A is CH, H10. Okay? They say it reacts with 3 equivalents. So what that tells you of hydrogen, so what that would tell you is that compound A probably has a combination of double bonds or triple bond, okay? So let us see here, to give compound B, and the formula for compound B is CH, C8, H16. Okay. Now, if you follow the index of hydrogen deficiency, the first thing you need to do here, determine the index of hydrogen deficiency. Which we abbreviate as IHB. Now, if you use the IHB formula, just to remind all of you, which is this here, carbon number of carbon minus number of hydrogen divided by 2 minus number of halogen divided by 2 plus number of nitrogen divided by 2 plus 1. If you use that formula, the IHB for this here, for compound A is 4. Okay? Okay, using that formula here. Now the IHB for, what happened here? I lost my hydrogen here. Oh, okay. The IHB for compound B equals to 1. So what does that tell you about compound A? What does that tell you about compound A? Because they've told us that they use 3 equivalent of hydrogen. That means all of the double bonds and triple bonds are gone. So what does that tell you about compound A? Anybody? Okay, let's see here. Let me see. Okay, what does it tell you about compound A? Oh, as a ring. Okay, okay, I'm sorry. Compound A as a ring. Very good. So it tells us that compound A must have a ring. Okay, so let us have that here. Ring. Okay, so compound A must have a ring. Very good. Now, it then says compound A also reacts with sodium amide followed by bromomethane to give compound C. Okay, what does that say? Say this here. Say it does this, sodium amide, and then followed by bromomethane to give compound C, which is this formula here, C9H12. So we have added one more carbon. Okay. What does that tell you about compound A based on this reaction here? Excellent, excellent. So that tells us compound A must have a terminal alkyne. Okay? So let us follow this logic here. Terminal alkyne. Okay? So we know compound A as a ring. We now know compound A as a terminal alkyne. Okay? But we only have 8 carbons here, so let us continue. It then continue to say compound A also is known to contain a cyclopentyl ring. This problem is solved. Now they say compound A has a cyclopentyl ring, so it also, we already said that it has a ring, so now that has been confirmed. So they now tell us it has this ring. That's that ring. So what is left here? Okay, compound A only has 8 carbon atoms. They've given us 5 carbon in the ring system, and we also know that it has a terminal alkyne. So at this point, I will say the chances are compound A must have this here. Now let me do better than that so that everything is not crowded up. I will say, okay, just bear with me now. At this point, I will take a guess that compound A at least must have this. Okay, that's your terminal alkyne. That's your cyclopentyl ring. So now this methylene group, all I'm doing is just adding this here because compound A only has 8 carbon atoms. If you count this, 1, 2, 3, plus 5. That's 8. Okay, let us continue. Now it says, finally, compound A reacted with potassium permanganate to give a ketone plus other compounds. Okay, so now it says compound A so it now tells us, we already know about all of this, so let me take all of this out of the way. We've already said that it's something like this, so let's take this out of the way. How did we know A had a terminal alkyne? Because of the reaction with sodium amide, followed by bromoethane, okay, bromomethane. That is the sodium amide will react with a terminal alkyne. Okay, so now they tell us, I was answering somebody's question, say, how do we know that compound A has a terminal alkyne? Okay, they now tell us compound A also react with potassium permanganate to form a ketone, okay, to form a ketone, plus other compounds, Okay, so at this point, the only thing missing here, remember that we said compound A has an IHD of 4. Okay, we know that it has a terminal alkyne. We know it has a ring. So therefore, it must also have a double bond. Because if you look at this here, the terminal alkyne, that is IHD of 2. The ring is IHD of 1. So that is a total of 3. So therefore, there is one more IHD here, which must be a double bond. So I would say, is it possible that compound A could be this double bond here? Okay, because of this reaction here, you say we could get a ketone or other compounds, or compound A could be this. Any one of these will do. Let me get this out of the way. I would say this could be compound A. This is compound A. Because if you react this with compound A, what do you get? You get this ketone here. Because this reagent here will cleave a carbon-carbon double bond, and the carbon of the carbon-carbon double bond that does not have an hydrogen becomes the carbonyl of a ketone. So that ketone could be this. And that will be consistent with everything they've given us. Okay? So this is compound A. So therefore, compound B will be, once you react with the hydrogen, compound B will be this. All of the double bonds and the triple bonds are gone. That will be compound B. And then compound C will be when you remove this hydrogen and then you react the acetylide with bromomethane, okay, which is this here. Then this will be compound C. Let me write this better here. Okay, so this will be your compound C right here. This compound C. And this is your compound B. and this is your compound A. Now, notice what we've done here. This is a case in which you need to know your reagents. If you don't know your reagents, you cannot do this. Then once you know your reagent, then you begin to now use your own critical thinking skills. Okay? So this is not a case of simply just knowing your reagent. Instead of having a 3-carbon attachment to the ring, could it also be a 2-carbon attachment along with methyl attachment? No, the methyl attachment must be to this carbon here because of this reaction. Okay? So I am responding to the questions that somebody is asking. This methyl group must be attached to this carbon because that is what this reagent would do. Okay, so anyway, think about this. Most of these questions are mostly knowing your reagents. The roadmap question does require that you do some critical thinking. Okay, so let us go to the last one, 14, because it's past 9, and I don't want us to stay too long. Because if we stay too long, it would take me too much time to actually process the file to the video. Okay, so I do want us to leave here maybe in about 10 minutes. Let's go to 14. Let me see. Okay, Masha, can you go ahead and read this for Masha Cake? Read this for us.
Starting with ethane and using a Grignard reagent and a ketone in your synthetic design, provide a synthetic scheme for 2-bromo, 2-methylbutane.
Okay, thank you. Very good. Okay, so now in this question here, this is a synthetic problem in which they want us to start with ethane and using a Grignard reagent and a ketone, and then to make this compound here. Okay, so let us see what that is. In other words, they want us to go from here to here. 2-bromo, 2-methyl. Bromo, methyl. Now, this is another case. We are now going beyond knowing your reagents. Keep in mind that the first 5 questions we did was just knowing your reagents. Now, once you know your reagents, then you should now begin to now do a synthetic problem. This is here where you're now putting together a sequence of reactions to go from one particular starting material to the product. Okay. They want us to use a Grignard reagent. They also want us to use a ketone, starting with this here. Now, if I was you, I would say, okay, if we have to use a Grignard reagent, and we are starting with this compound here, is it possible that that could be this part of this molecule? Okay? If we make a Grignard out of this, can this be part of this molecule? Let's say, yeah, that is possible. And then we also ask ourselves here, we want to make a tertiary alkyl bromide. There is no way we know right away to make a tertiary alkyl bromide using a Grignard. So therefore, however, we do know that we could make a tertiary alkyl bromide from an alcohol. Okay? So now the question you need to ask yourself is, since they tell you to use a Grignard, right now everybody must know that a Grignard will react, that you must know, with a ketone to give a tertiary alcohol. Now, if you don't know this, you can't do this problem. You are completely out. Okay? But once you know that a Grignard will react with a ketone to give a tertiary alcohol, then the problem is solved. Because you know now, from your tertiary alcohol, you could go to your alkyl bromide. Okay, so how do we start? We want to start with this here. Okay, for you to make a Grignard, you need an alkyl bromide or alkyl chloride. Okay, so I'll say, okay, I do bromination, the presence of light. And then I make my Grignard. Magnesium in ether. So I make my Grignard. Then they say use a ketone. I will say, okay, is it possible that this part of the molecule could be coming from a ketone? Okay? If that is the case, then I want to use a ketone that contains 3 carbon atoms. Okay? So I say step 1. In that case, I use acetone. This ketone here. And then keep in mind, once you react the Grignard with a ketone or aldehyde, then you follow that up with acid, dilute acid. Step 2. And that would therefore give me this. And the ethyl is coming from the Grignard. Okay, now once you form your tertiary alcohol, what reagent do we need to now make the product? What reagent do we now need to make the desired product? Anybody has an idea? How do you know A as? Okay, no, that I answered that question already. Okay, PbR3, excellent, excellent, excellent. PbR3. Now use of PbR3, that would, no, not PbR3, no, I'm sorry. PbR3 is good with primary or secondary alcohol. At this point, you need HBr gas. HBr gas. Okay, keep in mind, PbR3 will transform a primary alcohol or a secondary alcohol to the alkyl bromide. In other words, we'll replace the OH of a primary alcohol or secondary alcohol with a bromine atom. But if you want to replace the OH of a tertiary alcohol with a bromine atom, what you need to do here is to use a HBr gas, okay? And that will give you this here. So I think we basically use all of the reagents in this chapter. So this is I hope this is a good review for all of you. And okay, so this is an example of a synthetic scheme. Okay, what have we done? We went from the ethane, did a series of reactions to get to this here. Now, keep in mind now, do not just memorize this. This could be I could give you any synthetic problem similar to this. Don't simply say, oh, it gave us ethane, so therefore I will be looking for ethane. No, do not do that. Okay, all you need to do is know the concept. Okay, you said PbR3 is for primary and secondary alcohol. Yes, that is what I said. It's step 1 homolytic cleavage. Step 1 is homolytic cleavage, but do not forget that I'm not asking for mechanism. Okay, somebody is asking, it will be homolytic cleavage. Yes, anytime you see light right here, that means you are dealing with a free radical mechanism. But at this point, I am not asking for reaction mechanism. Okay? So, folks, I think we have come to the end of this session. Hopefully, you benefited from this session tonight. And what I will try to do, I will process this video. It takes about 4 hours to do that. So before 12 o'clock tomorrow, I will make sure that I post the video in Blackboard and also in YouTube. Okay, so I will send you an email message to that effect. And I will also stay behind for another 5 or so minutes for those of you who want to stay behind and ask me questions off the record. So I'm going to turn off the recorder now, and so the session will be officially over. Okay, is there any question before I do that? By the way, I see a lot of you. Let me give all of you that I did not call. Oh, I will be in my office by 2 o'clock tomorrow. Let me go ahead and acknowledge all of you who are here now. I did not call you during the session. I see Amit is here, Annette Levy, Vonlea Rickerson, Shante Smith, Christian Bradley, Danutika Gelling, Delano Ankins, Emeka is here, Erin McGee, Ganesh Mohan, Jasmine Lyons, Jerome White, Gillian Pelling, Jodwina Gassin, Kiara Wallace, Lauren Kibet, Mian Reyes, Makiba Walker, Malaysia Jalis, Mashake Hutchinson, Nolan English, Rachel Braham, Robin Onuaha, Robert Moore, Ronel Raymond, Sachin Vaskiren, Sean Taylor, Sipora Christopher, Victoria Faulkner, okay, and Victoria Faulkner. So I do want to thank all of you for coming in on a Sunday night to review organic chemistry. So until I see you tomorrow, enjoy the rest of your evening. Yes, somebody say, can you use 8BR gas for tertiary aqua? Yes, that is correct. Okay, so I will stay behind for another 5 minutes. In the meantime, let me turn off the recorder.